Alright, so today we're going to move on to section 3.3, which is evaluating limits analytically. We saw in the warm-up today in class, as well as a little bit of the video notes last night, the idea of direct substitution, and that's what we're going to be focusing on today. This is we'll say the meat and potatoes of evaluating limits, which is direct substitution or evaluating them analytically. And then what happens if direct substitution doesn't work right away. We'll look at some algebraic techniques we can use to still evaluate the limit. Because as hopefully maybe you noticed that using the calculator in a table or a graph are not necessarily the easiest way, and sometimes we might not have a calculator with us. Okay, so I gave you that sheet that gives you a bunch of properties about limits. That way you don't have to copy them all down. We'll just talk about them. So the first one, theorem 3.1, some basic limits. Let b and c be real numbers and let n be a positive integer. Then the limit as x goes to c of b is b. The limit as x goes to c of x is c. And the limit as x goes to c of x to the n is c to the n. Hopefully that makes sense. So if we have the limit as x goes to 3 of 4, what is that going to equal? 4. Very good. The limit as x goes to 2 of x, what is that going to equal? 2. Excellent. The limit as x goes to 5 of x cubed is 125. Nice job and good work with the dramatic pause. Thank you, I appreciate that. And again, just to emphasize, these should make sense. So the limit as x goes to c of b, well, b is just a horizontal line at whatever height b is. So the limit is going to be that value. If x is our function, that's a line with a slope of 1, a y-intercept of 0, and so the height is going to be the same as the x value. And if x to the n is a function, that's a polynomial, it's continuous. So I know that as I approach from the left and the right, it's going to be whatever the y value is of that polynomial when I plug in the x value. Alright, moving on to some other properties. So let b and c be real numbers, let n be a positive integer, and let f and g be functions with the following limits. The limit as x goes to c of x to the of f of x equals L, and the limit as x goes to c of g of x equals k. So then we have a scalar multiple. So the limit as x goes to c of b times f of x is b times the limit as x goes to c of f of x, which is b times L. We can see the sum and difference, which is just the sum and difference of the limits. The product is the product of the limits. The quotient is the quotient of the limits. Again, we can't divide by 0 though, so assuming k is not 0. And the power is the power of the limit. So again, those are all on your sheet. Just know them and understand them. They should make sense though. They're pretty straightforward algebra. So here, if you're given the limit as x goes to c of f of x is 3/2 and the limit as x goes to c of g of x is 1/2, I want you to evaluate the following limits. So pause the video, unpause when you're ready to check your work. Alright, so using the properties, I know the limit as x goes to c of 4 f of x is 4 times the limit as x goes to c of f of x, so 4 times 3/2, which is 6. When I have the addition, I add the limits, so 3/2 plus 1/2 is 2. Multiplication, I multiply the limits, 3/2 times 1/2 is 3/4. The exponent, or power, so I raise the limit to a power, 1/2 cubed is 1/8. The quotient of the limits, 3/2 over 1/2 is 3/2 times 2 over 1, which is 3. And this is another version of the scalar. It's the same as multiplying by 1/6. So 3/2 over 6 is 1/4. Alright, next, theorem 3.3, limits of a polynomial and rational functions. If p is a polynomial function and c is a real number, then the limit as x goes to c of p of x is p of c. We actually saw that earlier on. An example of that is right here. X cubed is a polynomial, and we plugged in 5, so it was 5 to the 5 cubed. Here, x is also a polynomial, so we plugged in 2, and we got 2. So we've seen examples of this already. This is just formally stating it for polynomials. The same is going to be true for rational functions. So if r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c does not equal 0, then the limit as x goes to c of r of x equals r of c, which is p of c over q of c. Again, the denominator can't be 0 though. Alright, so here's a polynomial function. I want you to evaluate the limit as x goes to 1. Pause the video, unpause when you're ready to check your work. This should not take very long. Alright, so plug in 1 and I end up with a limit of 5. Now one thing I want to point out, so you may be asking yourself, wait a minute, why aren't we checking the limit from the left and the right like we did yesterday? Well, we're understanding that a polynomial function is continuous from left to right, or right to left, it doesn't matter, and so I know that if I plug in 1 and I get 5 here, and it's a polynomial, then it's going to approach 5 from the left and the right, and that has to do with properties of polynomials. Alright, another example, the limit as x goes to 3 of 2x minus 3 over x plus 5. So keep in mind that when we're dealing with rational functions and direct substitution, we have to look out for the denominator equaling 0. So if that happens, then we'll talk about some other things that we can possibly do. So pause the video, evaluate this limit, unpause when you're ready to check your work. Alright, so in this scenario, that situation did not happen, the denominator did not equal 0. We were able to evaluate the limit by direct substitution and we got 3/8. Next, again, just another property on your sheet. The limit of a function involving a radical, so let n be a positive integer. The following limit is valid for all c if n is odd, and is valid for c is greater than 0 if n is even. So the limit as x goes to c of the nth root of x is the nth root of c. Again, that should make sense. So now we're going to look at the limit of a composite function. So if you're given f of x is 2x squared minus 3x plus 1, and g of x is the cube root of x plus 6. First, let's find the limit as x goes to 4. So the limit as x goes to 4, we can do direct substitution. And that's 21. Now, what is the limit as x goes to 21 of g of x? So again, direct substitution. So 21 plus 6 is 27. The cube root of 27 is 3. So what is the limit as x goes to 4 of g of f of x? Well, I can still just do direct substitution. I know g of f of x is just going to be the cube root of 2x squared minus 3x plus 1, and then plus 6. So now I'm just substituting in 4 to that. We actually already know what this is from our previous two evaluations. This is going to be 2 times 4 squared minus 3 times 4 plus 1 plus 6, which is going to equal 3. Alright, limits of some trig functions. So I want you to evaluate these limits. Pause the video, unpause when you're ready to check your work. Quick hint, don't freak out because it's trig. And now I know you're going to freak out because I told you not to, but don't. Okay, so here we can just do direct substitution for all of these. The tangent of 0 is 0. Pi times the cosine of pi. Well, the cosine of pi is negative 1, so that's negative pi. The sine of 0 is 0. 0 squared is still 0. Alright, next one. Evaluate the limit as x goes to 2 of 2 minus x over x squared minus 4. Pause the video, unpause when you're ready to check your work. Alright, so the answer here is negative 1/4, but let's see how we get that. So if we first try direct substitution, we end up with 0 divided by 0. This is what we call an indeterminate form. It means that we're not sure what the limit is, but we can maybe do some more work to find it still. So we're going to try some algebra. So whenever you end up with 0 divided by 0, you want to show that, and then do some more work from there. So in this case, that more work is over here on the left. So I factored out a negative 1 in the numerator, and I factored the denominator as the difference of 2 squares. The x minus 2's cancel, and so then I'm left with the limit as x goes to 2 of negative 1 over x plus 2. Now I can do direct substitution. Negative 1 over 2 plus 2 is negative 1/4. So now let's talk about, well, what happened at x equals 2 in the original function? Think about it. What was it? Very good. That was a hole. So, well, what was happening at the hole, or where was the hole? The hole was at 2, negative 1/4. Remember that to find the y value of a hole, you reduce the function and use the reduced function. So that's how, and now let me say it. I could verify this also using a graph or a table, but I should understand, if I know that there was a hole there, that from the left and the right, the function was approaching negative 1/4. The function just did not exist at that point. So if I asked you to evaluate the function at 2, it does not exist, but the limit at 2 does. So let me write that out using notation. F of 2 does not exist, but up here we can see the limit as x goes to 2 of f of x is negative 1/4. Alright, so I want you to try to evaluate the limit as x goes to 4 of x squared minus 5x plus 4 over x squared minus 2x minus 8. Pause the video, unpause when you're ready to check your work. Alright, so here, when we first plug in 4, we get 0 divided by 0 again, so our indeterminate form. Factor the numerator, factor the denominator, x minus 4's cancel. I have a reduced function of x minus 1 over x plus 2. Now I can do direct substitution. I end up with 1/2. So the limit as x goes to 4 of this function is 1/2. Another burning question in your head right now, I'm sure, is, well, how much of this work do I have to show? Everything that I showed here on this page, you should be showing on a test or a quiz. Next one. Evaluate the limit as x goes to 1 of x cubed plus 1 over x minus 1. Pause the video, unpause when you're ready to check your work. Alright, so here when we initially do direct substitution, we end up with 2 divided by 0. That is not an indeterminate form. Now, just to point out, well, what if I tried to factor and simplify? The numerator does factor, it's the sum of cubes, so it factors into x plus 1 times the quantity x squared minus x plus 1. Remember, this will never factor into real coefficients if this was from the sum of cubes or the difference of cubes. Nothing cancels, so the limit does not exist. Well, what happened at x equals 1 on this function? So let's think about that. It's not a hole. If it was a hole, we would have been able to eliminate it. So if it's not a hole, what was it? Vertical asymptote. And we can see that if we look at the graph or a table. So here I put the function in, and I can see as I approach 1 from the right, the function is going down. As I approach 1 from the left, the function is going up. I can also see that in the table here, so I put in these values. These numbers are going down, these numbers are going up. Those are not approaching the same value, they're not even approaching a value, they're approaching negative infinity and infinity. Alright, next one. I want you to evaluate the limit as x goes to 0 of the square root of the quantity 2 plus x minus the square root of 2 over x. Pause the video, unpause when you're ready to check your work or when you get stuck. Okay, so here we got the indeterminate form again, and now maybe you have not seen this technique before, so you might have gotten stuck. That's okay. But here we want to rationalize the numerator. So anytime you see this sort of format where you have roots in the numerator like this, and you get the indeterminate form, that's a big hint that you're going to rationalize the numerator and things should hopefully work out. Not always, but hopefully. What does it mean to rationalize the numerator? It means multiply the numerator and denominator by the conjugate of the numerator. So I multiply by root 2 plus x plus root 2 and root 2 plus x plus root 2. Now when I multiply out, the numerator just becomes 2 plus x minus 2. The 2 and the negative 2 cancel, leaving just an x in the numerator, and that x reduces with the x in the denominator, which is what I want to happen because I need to get rid of the 0 in the denominator. Now I'm left with the limit as x goes to 0 of 1 over the root of 2 plus x plus root 2. Now I can do direct substitution, and I get 1 over 2 root 2. Remember, we need to rationalize when we have numbers under the root, but we do not need to rationalize when we have variables underneath the root. So I rationalize and I get root 2 over 4 as my answer. Again, you may be asking yourself, how much work do I need to show? You need to show all of this work. Especially show this step here. I want to see what you're doing. Alright, we're running out of time on this video. There is one more example I want to show you, so there's going to be a part 2. I apologize. But so this one's done. Go to part 2. There's just one example there, and then we'll conclude this lesson.